Hello everyone, thank you so much for coming to this presentation. My name is Peizhu Qian. I'm a PhD student studying computer science at Rice University. I work with Dr. Vaibhav and Unhelkar on problems related to human-robot interaction, explainable AI, and human-centered AI. Have you ever wondered how it is like to be a firefighter? Interestingly, firefighters have a work schedule much different from many other industries. In most cities in the United States, firefighters work 24-hour shifts, and they work 10 of the 24-hour shifts per month. This means that firefighters may need to work in highly stressful situations while being tired and sleep deprived. In late 2020, the city of Los Angeles became the first city in the country to add a firefighting robot to their rank. The Los Angeles Fire Department chief described the robot as a game changer to their team. Handling emergencies require firefighters to react quickly and be prepared to any fast-changing situations. During such situations, firefighters want to make sure they do not waste their time figuring out how the robots work, but use the time to fight fire. So in order to work effectively with robots, robot users, who are the firefighters in this example, need an accurate mental model of the robots they work with. Having the correct mental model of the robots will ensure safety, avoid unintended side effects, and build users' trust in robotic systems. To help formalize the problem of acquiring accurate mental models, let's look at a simplified version of the firefighting robot. The robot is operating in a rescue environment, which includes debris and fire. The firefighter wants to deploy the robot to fight fires. However, without any prior training, she is unsure of how the robot will act in a new situation. Will the robot fight the fire as soon as possible, or will it first clear the debris and then proceed to the fire? In practice, the autonomous robot behaves according to its policy. It clears the debris first and then fights the fire. To consider sequential tasks and uncertainty, we assume that the robot behaves according to a Markovian policy. This policy may be arrived at using reinforcement learning, planning, or even handcrafted. We do not assume the policy to be optimal or make any assumptions about how it is calculated. To use the robot correctly, the user should have the correct mental model. Otherwise, the robot may introduce delays in fighting fires. We define user model as a probability over different user policies. Prior to training, the user may not have the correct model. In this example, the firefighter holds two hypotheses about the robot's policy. In the first scenario, the robot clears the debris, then puts off the fire. In the second scenario, the robot goes around the debris and directly goes to the fire. So which one of these hypotheses is the correct robot policy here? In our framework, we represent different user hypotheses using a belief over possible robot models. Then we update the user's belief using Bayesian theory of mind. Our research looks at training users of robots so that they have accurate mental models. Our goal is to train users prior to task deployment, so that they have the correct belief over robots' behavior and so that they can accurately evaluate what the robot will do in a novel situation. In this example, before training, the firefighter holds a uniform belief over the hypotheses. But after training, we want the firefighter to have a probability of 1 over the correct robot policy. To summarize, our research problem is to train users to have an accurate mental model of the robots they work with. To categorize the research in this emerging area, we view it from the lens of pedagogy. Researchers in pedagogy have examined a variety of teaching strategies for the setting of human-to-human teaching. One categorization of these strategies is based on the use of direct versus indirect instructions. For example, when we go to lectures are a form of direct instructions. These instructions are prepared before classes, and they often aim for a large general audience without much independent or personalized learning. Prior work in Explainable AI has mostly focused on generating direct instructions from a robot policy. On the other hand, sometimes we look up tutorials or practice problems on our own, and these are a form of indirect instructions. These instructions target the specific questions we have as an individual student, and they involve a high level of personalization and independent learning. Both types of instructions are effective pedagogical methods, but both approaches are missing key features. Direct instructions are missing the independent learning and personalized features, while indirect instructions are missing the guidance from an expert. Recognizing these limitations, our framework adopts a hybrid teaching strategy where the AI teacher first generates instructions before interacting with the user. These instructions are generated based on a cognitive human model, and during the time where we are training the user, users can create their own scenarios in an environment and self-explore what the robot's actions would be in the specific scenario they created. We formulate the problem of generating direct instructions as a sequential decision-making problem, and generate instructions using Monte Carlo tree search. In contrast to prior direct techniques, our approach can consider stochastic environments. Here we provide an example for training robot users with our approach. We can use an interactive user interface like this, which allows users to request personalized instructions. This is a simulated research and rescue domain. The user is customizing the robot location in order to learn about the robot's objectives. This user located the robot in the middle of a patient, fire, and debris. Then requests a custom instructions from the AI teacher. Then the AI teacher shows the user that the robot moves up first towards the debris and the fire. To evaluate our approach, we conducted an odds of wizard experiment, as well as user studies with 24 participants from Rice University. We designed 3 robotics tasks, all inspired by real-world applications. The first task is a search and rescue robot. The second is a navigation robot, and the third is a recycling robot. For each task, we allowed 25 instructions to learn about the robots. The objective of the user study is to evaluate the effectiveness of our hybrid approach. The independent variable in our evaluation is the training strategy. The first training strategy is direct, which gives participants 25 direct instructions generated using prior art. The second method is hybrid, which allows a total of 25 pre-generated and user-selected instructions. The users can decide how many of each type of instructions to receive. And the third training strategy is indirect, which allows participants to request 25 user-selected instructions by interacting with the AI teacher. The dependent variables in our evaluations are first, accuracy of users' mental model, which is evaluated by asking users to predict robot behavior in previously unseen scenarios. The second dependent variable is users' preference of training strategies. This is evaluated through post-experiment subjective surveys. After learning about each robot, a participant receives a set of questions asking them to make prediction of the robot behavior in scenarios that they have never seen before. Other than the objective evaluation, we also ask participants to rank their learning experience. The left graph here shows that the hybrid strategy results in higher scores than the direct strategy in predicting robots' actions. The graph on the right shows that the participants have a better learning experience with hybrid than direct. We also notice that hybrid strategy performs comparably to indirect strategy. This trend indicates that human users are capable of identifying critical states that provides the information about the robots that they are previously unaware or unsure of. We posit one reason for the observed performance of the indirect strategy, which is that users know what they do not know better than the user model used by the AI teacher can predict. and thus the participants can choose instructions as effectively as the AI teacher. Through the post-experiment survey, we ask participants to select their preferred method of instructions and the ratio between direct and indirect instructions. 3/4 of the participants indicate that they prefer to receive both direct and indirect instructions and choose the relative proportion of each instruction type themselves rather than having an AI teacher to allocate the teaching budget. In this work, we highlight the utility of interactivity in AI transparency and explainability. Interactive teaching of agent behavior to humans can reduce the amount of time it takes for humans to create mental models of these agents, improve the performance of human AI teams, and reduce the catastrophic effects caused by poor understanding of AI systems. In absence of interactivity, users are not able to clarify user-specific confusion with only direct instructions. We demonstrate through a user study that indirect instructions can address the needs and preferences of individual users. Future XAI systems should leverage on humans' ability of self-exploring and independent learning, while providing guidance through computational methods to generate direct instructions. The community can consider diving deeper into studies from education and psychology to design helpful interactivity features. Building on the insight of interactivity, we provide a novel interactive, explainable AI framework called the AI Teacher and validated using a detailed user study. Currently, we are working on more realistic systems and are actively looking for collaborators and applications in realistic environments.